Hello everyone, and welcome to this presentation entitled Simulation of Stainless Steel Synthesis. In this video, I would like to show you how we simulate this process using FACSage. More specifically, I will show you how to properly select the different phases in the FT oxide and FT databases, and also the different conditions that are necessary to impose to simulate the various processes. And then we can compare with some practical results that we have already obtained. I hope you will enjoy it. So, a little bit of context here. The simulations that I will be presenting, they are related to a project that came from a demand of Hydro-Québec. So, we know that hydraulic turbines, they are critical components in hydroelectric power stations, and most of them they are made of C6MM, which presents appropriated mechanical properties considering the requested impose of the turbines. So this study aims at understanding and quantifying the impact of the presence of critical impurities on the formation and also precipitation of inclusions in this stainless steel. So for that, we needed to develop the samples that we would be studying. So we could synthesize samples with different levels of oxygen or sulfur, and also test different deoxidizers and even verify how the duration of the melting process could impact on that. So here I'm showing the basic steps that allow us to produce stainless steel out of liquid metal. First, we have the alloying process when the material is melted and alloyed. Then it goes to the cast process where it cools and solidifies, and this as-cast structure needs to go through a process of heat treatment in order to lower the hardness of this material and obtain the desired characteristics. So, we have been working on the synthesis of the samples for this project in a collaboration with CNQ, which is the Quebec Metallurgy Center. I don't know if we have steel makers or steel producers among our attendees, but what is important to mention here is that the CNQ, they have induction furnaces, but we don't have the availabilities of the technologies that are used in industry to be able to produce in the state-of-the-art the stainless steel. So we are trying to use raw materials that are really pure to be able to synthesize the samples by performing mass balance calculations to reach the best composition possible. So here we are trying to mimic the inclusions that would form in a commercial stainless steel. So what I'll be focusing on during the simulations is the link between the practical results that we have already obtained comparing to the chemical specification of chemical composition of the alloy and the resulting phase assemblage that will be directly impact the performance of the material. So, more specifically, the examples will show the phase formations and the deoxidation process. Also, what information we can obtain from these calculations. Okay, so in this project, we are looking at stainless steel that contains some chromium and nickel. So chromium is there to protect the alloy and to form an oxide layer at the top of the stainless steel. Nickel is there to improve the mechanical properties of the alloy, and then we have some other elements that also ensure the desired characteristics. So here we are working with the chemical composition that is required by the standards used by Hydro-Québec, and we performed a mass balance considering the raw materials that we had available in order to achieve this chemical composition. With these results, we used them as an input to FACSage. So in this calculation, we have the objective to verify the phases that will be forming in a range of temperatures that we'll set. In a second step, we will observe what changes when we have the presence of oxygen in the melt. So here is the FactSage interface, and we're going to be working in the equilibrium mode. The first step I will take in this simulation is to set the composition of the alloy. I have already added the elements here, so you can see the list of elements and the amount of each. So in this panel, we see that we have these elements, and if we click here, there are more. So I added here also oxygen, aluminum, calcium, silicon, and sulfur, but we can see that the amount is 0. So here we are using a gram base, and in case you want to work in a different base, you can change it here. Okay, so here in data search, I'm going to activate the FactPS for the gas phase, FT oxide for the formation of oxide solution, and FT steel. So that will be the database that I'm selecting. We can click in OK. Here we can click in Next, and then in this panel we are going to select the compound species, gas and pure solid. The solution phases, they are selected by default, and in temperature we can add the range. So we are going from 1600 to 600 by steps of 20 degrees Celsius. So I'm going to be selecting normal plus transitions. So we're going to have 51 calculations plus the transitions. Now we can run it by clicking in Calculate. Here in these tabs, we can verify the information related to each temperature. We are going to take a look at these last two transitions. So at this temperature, we have BCC phase only. So we can see that we have 100% of BCC. And if we take a look at 1487 degrees Celsius, we will have that we 100% of liquid. So we had to keep this temperature in mind when we were doing the synthesis of our samples. So to make sure that we had everything liquid and well mixed, we aimed at 1600 degrees Celsius. Another information we could check in this calculation are the phases that are in equilibrium. So we want to see the grams of all the phases that are forming as function of temperature. We go at the top in Output, we select Plot Results, and for the axis, we want to see the grams, okay, as function of temperature. So we also going to change it. Now we're going to have to select all the solutions and the compounds that we are forming. So we need to check the compound first. They should be in green. They are all 0. And then I'm going to look in the solutions and select the liquid, the FCC, the BCC. We have some carbide that's already selected. There is a phase forming because of the presence of phosphorus. And that's it. We can click in OK. And then plot. So here we can make some adjustments to better visualize the results. So I'm gonna double click here and change it so we can better see the formation of phase. Here at the bottom we have just a small amount of other phase that are forming. In case we want to verify, we can decrease the scale and check only this small content here. If we click in the line, we can see what's the phase that is forming. So here we have liquid, here we have BCC, and then FCC, as we selected previously. Now that we have checked it, what are the phases forming without the presence of oxygen, we can see what's going to happen if we have it in the system. So basically, we first need to identify what's the amount of oxygen that we need to add to the system. So we saturate them out. As we are adding oxygen, we're going to reach the saturation limit, and depending on the condition of the operation, we can either form a slag, a spinel, or maybe it could be in equilibrium with the gas. So this is one of the aspects of the project. So what is the phase that saturates them out and limits the amount of oxygen that we can dissolve in the liquid alloy? I'm going to try to evaluate that using the alpha parameter. So here for oxygen, we are going to add an alpha, and then we can press next. In the next panel, I select all the gas, all the solid, and all the solutions by default. So here I'm going to remove the alpha content, and I'm going to do a formation target in spinel phase. I already did some preliminary calculation, and I know that this is the phase that saturates them out. So I'm going to scroll down and look for the spinel, and then I'm going to put an F option here. So as a first guess of this solubility, I will use 0.02, and we are going to use the temperature of 1600 degrees Celsius and pressure of 1 atmosphere. We click on calculate. Okay, so now FactSage has evaluated the alpha value, as we can see here at the top. And if we scroll down, we can see that we have 100 grams of liquid. And if we go a little bit more down, we can see that the spinel phase forming with an activity of 1. So here we have 0 amount because it's not formed yet, but it's almost. So if we have more oxygen, then this phase will precipitate it. So I keep this alpha value that is required to saturate the liquid solution, and then I'm going to add this in the first panel. In our samples, when we synthesize it in the open atmosphere furnace, this was the concentration of oxygen that we have obtained, around 300 ppm. Now we can check if we have different phases forming with the presence of oxygen. So we're going to perform the same calculation and check the other phase that might form. With this information, we can compare with the results of the composition of the inclusions that we have found. So here we're going to keep the same selection for gas and pure solids. For the solution phases, we can click and select, and then clear all solutions, and then select again and select all solutions by default. And we can work with the same range of temperature from 1600 to 600 by steps of 20, and then we calculate. So we're going to plot the same graph as before. So we go at the top in output, select plot, plot results. Okay, for the axis, we want to see the grams as function of temperature, and we are going to select all the solutions and compounds that are forming. So we need to check for the compound first. They should be in green. Here it's all 0. And now the solutions. So we select liquid, the FCC, the BCC, carbide. We have some phase forming because the presence of phosphorus. And slag. And also spinel and rhodonite. So we click in OK. And we plot. So here we have the graph with all the phases that will be forming according to the temperature. The ones that are not identified, we can click on it and then click here and add label and confirm. Here we have slag. Okay. And what is interesting here is that if we look at the spinel phase as an example and we check like this temperature, we go back to the calculations, and then here we can check around 1200. We scroll down a little bit, so we will see that the spinel is forming, and here we can check the composition of this phase. We can see here that we have some chromium manganese oxides forming. So if we go back and check here, so we can compare here with the results of the SEM of a sample that we synthesized. So here we can see that mainly of the inclusions, they are the same type, chromium manganese oxide, and they present a very angular shape and the size between 4 to 8 microns. Now that we have verified the content of oxygen present in the melt, we can activate the deoxidizer and check how oxygen content will respond when we add aluminum, for example. So basically, we would like to understand how we can define the amount of deoxidizer that we will be using, so we can lower the amount of oxygen and hopefully get a cleaner steel. We are going to start with adding aluminum. So we put an alpha value and we click in next. We keep the same selection here, but then we add the value that we want to vary the alpha, which is the amount of deoxidizer. So we want to vary it from 0 to 0.1 per step of 0.01. We're going to use the temperature of 1600 degrees. And the pressure will be 1 atmosphere. So here we are adding aluminum in the melt, hoping that it reacts with the oxygen and decreases the content of oxygen into the melt. Now we can run the simulation and click on calculate. Okay, so we can plot now the amount of oxygen dissolved in the liquid metal as function of the alpha parameter. We go at the top in output, select plot results. For the axis, we want to see the wage percentage as function of alpha. And we want to plot it for oxygen now. So we need to select it here. So we go at the end completely, and then in the elemental balance, I'm going to activate the oxygen liquid. We can clear make sure that we don't have anything selected. Okay, so now I can plot the results. We go in OK and then plot. Here we're gonna work a little in the scale and change for ppm. So we go and edit, change scale, and then we multiply this for 10,000. We can also click on the label and then change it for oxygen. It's gonna be ppm method, and we're gonna work from 350 ppm as an increment of 10 and labels 20, and change the format also here. So we can see that it starts around 320 ppm, which is really close to the value that we were able to reach in our samples, and we can go as low as virtually this point here. And if we click in the lining, we can check the oxygen content according to the addition of aluminum. So here alpha will be the amount of aluminum in grams. So for 100 grams of steel, this is the value that we need to target if we want to reach this content of oxygen. Now we can also save this figure, so we can go and File, Save As, and use the name as you wish. And then you can add this image in a software that you are working with as a PowerPoint. Now that we have checked the evolution of the oxygen content in the liquid as function of the addition of the deoxidizer, we can also check the use of other deoxidizer. So we're going to keep the amount of 0.06 for aluminum, which is the amount that we used in our mass balance. And then in the next page, we're going to use an alpha parameter for calcium silicon. You can click in next. Okay, so here we are varying the amount of calcium silicon from 0 to 1 by steps of 0.01. We keep the same temperature here, so we're going to have 101 calculations. Okay, so we can check again the oxygen content. So we go in our plot results. In the axis, we're going to look for the wage percentage, and we're going to be varying the alpha from 1 to 0.1, and I'm going to click in OK. Here we are going to select the oxygen that is present in the liquid phase. We scroll down here, and then in the elements, we look for the oxygen here. And then we click on OK and plot. You're going to have to work in this graph, so we can come here in Edit and change scale. We're going to multiply it by 10,000. So we're going to have this X here in ppm. So we come here, and we already know that we have the presence of aluminum, so we're aiming at a very low content of oxygen at the beginning. So I'm going to select labels at 10 and correct the format here and press OK. Oh, before here I'm going to change the name. So this is going to be oxygen, ppm maxic, and then the alpha will be calcium silicon that will be added. And then we're clicking OK. Good. So here at the beginning, we can check that we already started with a very low content of oxygen, and as we add the calcium silicon, it's going to be decreasing a little bit more. But if we follow like the recipe, we would be adding maximum of 0.3 grams of calcium silicon, and this we will be reaching like a very low content of oxygen, as it is showed here virtually. Another information that we could check in this calculation is the phases that are in equilibrium. So we want to see the grams of all the phases that are forming as function of alpha. I mean, when we add this deoxidizer, calcium silicon, what would be the impact? So now with this calculation, we are simulating a higher amount of calcium silicon than what is required. So we can see where the oxygen is going to. So we hope it is transferred to the slag. So we're going to replot again, and then we're going to be plot again, and then change for grams. And then in select, you're going to have to select all the solutions and compounds that are forming. So we're going to be selecting the liquid. The slag, we have some oxide, corundum, and that's it. Okay, then we can plot. Okay, so this graph needs some improvements. I'm gonna work here from 1 with increment of 0.01 and labels of 0.05, and then adjust the format. So here it will be phase in gram, and the alpha is going to be calcium silicon, also in gram. We click on OK. We see that we have some phase here. This one at the monoxide, and this one is the slag. So we can see that as we add calcium silicon, the slag is forming, which means that it might be reacting with the oxygen forming the slag. But we also see the formation of this other phase. With that, we can say that we're not able to completely flux it. So now, with the proportion that we are using of aluminum and calcium silicon, we do not form a single phase. So we need to optimize this the aluminum to calcium silicon ratio. So maybe we can remove that and just form the slag. So in this example, the deoxidizer is not working perfectly. We need to adjust this proportion and pay attention to this while we are adding this, we're doing this addition. So to make sure that we don't add too much calcium silicon, because then we would be forming solid. With this same calculation, we could also check how the bulk composition of the liquid is. So we go in Output, Plot, plot results. And then in the axis, we're going to be selecting the wage, and then we're going to refresh and clicking OK. And you're going to see all the elements that are in the liquid metal. So I'm going to select the molybdenum, nickel, manganese, chromium, calcium, phosphorus, silicon, aluminum, oxygen, and carbon. We're clicking OK, and then we plot. So here we need to do some adjustments. So we're going to change the scale. So we're going to go for a maximum of 15 with increment of 0.5 and adjust the format and clicking OK. Okay, so here we can see that there is no evolution of the composition as we add the deoxidizer in a low amount. Basically, we are not impacting the global composition of the alloy, which is good. However, if we add too much, besides significantly increasing the amount of silicon, we are going to also impact other elements as chromium and nickel. And decreasing the amount of chromium or even other elements will not be good. So here we conclude the simulations with the deoxidizer agents. So we are at the end of the presentation. I would like to thank you for listening to it, and in case you have questions, they are welcome. Here you have my LinkedIn in case you want to contact me. Thanks.